right, so here's right, electromagnetic spectrum. All right, so where we left off, we're doing harmonic motion, but also waves, and that's going to lead to this. Light is a type of wave. It's a transverse wave, travels at the speed of light. But actually, like visible light is only one small part of a much larger phenomenon. And so we've got radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays are all part of this electromagnetic spectrum. So it's these oscillating electric and magnetic fields, right, that can travel through the vacuum of space, right? Because like light can reach us from the sun. Okay? And they all travel at the same speed, right, which is called the speed of light, 3 times 10 to the 8 meters per second. But really, the speed of light is really the speed of all massless particles. Anything that does not have mass has to move at that particular speed. It's called the speed of light because light was the first thing to be known to travel at that speed. Okay? But what your eyes can detect is only, again, like one small part of this. All the colors of the rainbow is just each color corresponds to one particular wavelength. And then some animals have eyes that can detect a little bit into infrared, a little bit into ultraviolet. So it'd be interesting to like get inside their minds and see like what colors are they seeing? Like what does ultraviolet look like? I've even heard that there's like some surgery that some people have gotten that like removes part of your eye where people can actually see a little bit into the ultraviolet part. Like your brain can actually interpret it, but somehow it doesn't like filter through normal eyes. So they report seeing colors that are really indescribable, right? Because like, how do you describe a color that no one's seeing, right? And yeah, each of these wavelengths and corresponding frequency. So the longer the wavelength, the lower the frequency. The higher the frequency, the shorter the wavelength. Okay, you guys know that from speed equals wavelength times frequency. That still applies here. Yeah, so each of these can travel through like some materials, but not others. For example, glass, right? Visible light can pass through glass, right? And there's reasons for that. We'll get to there's like a quantum mechanics explanation for that. But glass blocks infrared and ultraviolet, right? So if it's a really bright sunny day and you're sitting inside your car, you don't have to like wear sunscreen if you're like going on a like a road trip or something, right? Because your windshield will like block out most of the ultraviolet. Okay, yeah. Now, most of today actually, I want to talk about like optics and reflection. We're going to focus on. So there's different ways to go with this. We're going to hit at some point reflection, refraction, talk about color theory, like additive and subtractive color mixing. Got some labs lined up with Snell's law and the whole deal. Right, you guys see some new posters hanging around this classroom. Right, so let's go reflection. Let me bring in Paul Hewitt to show you guys how mirrors work, and we'll build from there.
Consider a candle. All optics books consider candles for objects, okay? Now we're going to look at the image that this candle gives in a mirror. Let's suppose right here, we have a mirror surface. Now what happens is light, let's just take from this point. Light goes in all directions. Some comes straight ahead, some comes up like this, some comes like this. The light hits the mirror in all directions. And when it hits the mirror, it, boom, reflects, yeah? And it reflects how? There's a normal, a normal, a normal, a normal. It reflects such that this angle, for example, here, will be equal to this angle here and reflect like that.
All right, so those dashed lines that he just drew, he was saying normal, right? What does normal mean again? Like a math term? Perpendicular. Yeah. All right. Yeah. So you guys remember that, right? If two lines are normal, they're perpendicular. All right. So the angles that we're measuring when we're talking about reflection, and later on when we get to refraction, it's gonna be the same story, right? If you got like a light ray crossing from one medium to another medium, right? We're interested in the ray that's normal to that, perpendicular to that. We're gonna start measuring these angles. Right now, for reflection, right? He's got a flat mirror here, reflection. Right? You guys see how the angle of incidence equals the angle of reflection, right? That is called the law of reflection. In fact, it's so basic, I didn't even have a poster for it. Just honestly, it didn't cross my mind to make a poster for it because it's just so straightforward, right? This angle has to equal that angle. That's pretty straightforward, right? Okay.
And up here, this will reflect right back to where it came, yeah? Because it hits flat, huh? Right angle. Huh? Up here, like that. And up here, like that. And down here, like that. Where this and this are the same. I don't have that drawn very well, huh? Like that. You get the idea? Now, you have your eye out here and you're looking. These rays here are all diverging. They're spreading out, see? They're spreading out this way, just as if they were this way. See, it's like this continued, huh? But that spread out looks to you like that ray came from back here, that ray came from back here, that ray came from back here, that ray came from back here. It looks to you out here like there's a flame here and also a flame back here. And I could draw the same rays for the bottom of the candle. That's done in your book a little bit, yeah? Okay. And the bottom of the candle, it would look to you like it's over there. And so you would see the candle here, and you would see the image of the candle. And let me ask you a question. What's the distance here, and the distance here? Begin with SS. Same, gang. Same.
All right, so go back to
the candle. That's done in your book a little bit, yeah? Okay. And so you would see the candle here.
All right, so if this distance is like 2 meters, then this distance would also be 2 meters. Okay, now that's true for a flat mirror, for a plane mirror. I mean, you guys are looking at plenty of flat plane mirrors that you guys know that would be the case, right? So we're starting off with a nice basic example, which has an outcome that you know what it's going to be. Right, but what about for something a bit wonkier? Like what about you guys know in front of my room I have one of these going on.
Extraordinary optical toy, one of the best ever made. This little piggy went to market. Well, I think it's a pig. It looks pink, and I should be able to pick it up, but it's just not there. I tried poking it. No, nothing there either. Of course, it's a mirage. But when I lift up the top parabolic mirror, there the piggy is really inside, quite real and quite solid. But when I replace the top and the parabolic mirror, there he is in a mirage form, looking as.
All right, and that's a really good effect. Right, so you switch back over here. All right, so I have one of these too. Doesn't work super well on the projection because you can't get the angle quite right. Oh, sort of looks a little ghosty pig, but I'll pass this around in case you haven't gotten to see this yet. And it really looks like, you know, to get it the right angle, it looks like there's like a pig hovering right above it. And so what's going on with that? Something to do with like how the mirror is curved, right? It's called a parabolic mirror. Okay? So see how far we can get on that today. We're gonna do some ray diagrams. And then we're bringing this equation and see how the equation matches with the graphical solution to where's the reflection going to be. Okay, so everybody has a paper. Does anybody not have a paper like this? Do we not have a paper? So everybody's got a paper, right? Okay. So let's call this ray diagrams reflection. You guys know reflection refers to mirrors. Okay. And this side of the paper, I'm going to focus on convex mirrors. So maybe I'll add that too. Okay. Convex. Okay. Write your name on your paper, because I'm going to have you guys turn this in. We should be able to do, my goal is to do 6 of these that I was able to do last class. So I think that'll work out. Okay. So you wrote your name, you wrote your title, ray diagrams, doing reflection, same thing as mirrors. Okay. And the side of the paper, we're going to focus on convex. Okay. That UFO pig parabolic mirrors then passed around. That's actually a concave situation, so that'll be a later class. Okay. Okay. Then across the center of the paper, do a dash line. We're going to fit in 3 ray diagrams on this side, and we'll do 3 ray diagrams on the back. So then about a quarter of the way up, do a dash line, and then down here, a quarter from the bottom of the page, do a 3rd dash line. You guys got those 3 dash lines? Yeah, so it's lots of rulers, of course, going around. If you don't have a ruler, then maybe have a notebook or a folder, or maybe you can take another piece of paper and like fold it in half and like use that as a straight edge. All right, let's put some mirrored surfaces here. Okay, let's have one surface like this. So here, maybe there's another one's like more tightly curved, but it's the same idea. Okay. And for the third one, I'm actually gonna do the maybe get a slight curve and put it kind of close to the left side of the page. About like that. So you guys using a straight edge or ruler to make those lines. Right, you guys have some mirrored surfaces about where I put them. Okay. All right. Next thing, I need some like object. Okay. Now, Paul Hewitt was using candles. Candles are common. Some textbooks use arrows. I don't really like arrows because we're about to draw like a bunch of like arrow-looking rays. That's kind of confusing. I like stick figures. I've always used stick figures, so I'm going to keep using stick figures. Draw a stick figure right about here, right, standing in front of this mirror surface. Okay, so this could be like a funhouse mirror, right? Or how about this? You guys ever look in the backside of a spoon? This be like looking in the backside of a spoon, right? And what does that look like? Right? Maybe you know from from memory, from past experience. Do you think you see a reflection of yourself that just looks really tiny? You're like right side up and you look really tiny. Right? That should be the outcome of this one. Right? But we're gonna see. Now, one thing that we have to answer is like, well, how curved is this? Like, how can you quantify how curved it is, and how could you represent that graphically? Okay? So let me go off this page a little bit. I'm gonna come back to this. Just filling some extra notes for you guys here. All right. So we're talking about parabolic mirrors. Suppose you have like so you have like a spherical mirror. Now a sphere is not the same shape as a parabola, but you might have a parabola that could like align flush to a sphere, like at some point, right? You got like a parabola lines flush to the sphere, okay? And the sphere could have, make like a giant eared sphere, if you could think of it that way, right? It has some radial size r. That could be like r for radius, right? Radius. Go ahead and spell that out, radius. Okay? And as the light rays on the mirrored surface coming from like over here, like bouncing off the surface, right? They're all different directions, like boing, 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 right? Off these surfaces. It's like, well, they're all individually going to follow the law of reflection, okay? Which is they're going to bounce off the same angle of reflection as the angle of incidence, okay? With respect to like each normal line, right? Now you guys know each normal line is like gonna be a little bit different angle for something like this, right? It's like a curved surface. So here's like a bunch of normal lines. Right? They like gonna change direction a little bit, right? So how are we gonna be able to align like what direction the rays are gonna bounce off, right? Well, we need something called a focal point, right? And the focal point is always halfway between the surface and the actual radius of the sphere that would fit flush to the parabolic surface. Okay? So I'll label that F for focal point. Okay, it's gonna help us make these ray diagrams. Okay? And later on, I'm also going to break out an equation that deals with the location of the focal point. And I'll also call it F in the equations, but it's going to refer to the focal distance. Right, so like F could be focal distance also. Okay. So just for context, if you see a single point labeled F, I'm referring to the focal point. In the equations, when you see F, it's like, oh, F is like so many centimeters. Well, I'm talking about like this distance right here, like from the surface to that point. Okay, look at that. Okay, so here's some equations. Okay, the focal length, focal distance or focal length is always 1/2 of the radial size. Right, of that circle. And right, here's an equation that we can test later, like after we draw these diagrams. 1 over the focal length, right, 1 over the focal distance, is equal to 1 over distance of the object plus 1 over distance of the image. I think it's that poster over there on the wall. So that, okay, to find the image location. So you guys know F is focal, focal length or focal distance. Okay. D sub O is distance of object from the surface. And D sub I is distance of the image from the surface. Okay. Okay. So we'll do the ray diagrams, then we're going to come back to this equation. We're going to test out, see like, is that really consistent with that? Okay. You guys got that? All right, so let's go back to these ray diagrams then. Diagrams. Okay. So here's this guy. Now I'm gonna switch ink color. You don't have to. You could just keep using the same pencil or whatever you're using. Okay. I need some light rays. Oh, whoops! I forgot to draw a focal point. Okay, let's define the first focal point as how about like back here? I'm just doing a random location. So that one. Okay. Okay. So let's see where these light rays are going. And I'm gonna have one light ray that skirts the top of this guy's head. That's parallel to the ground. Now you guys know there's like a million bajillion light rays bouncing all different directions, okay? Off the sky, off the surface, going all different ways. Okay? But you only need to follow a couple of light rays to figure out where the reflection is going to be. So I'll show you guys a procedure that we're just going to copy paste this procedure over and over, but it's going to give different outcomes for different mirrored surfaces. So here's one light ray. Maybe we've got a laser beam and just parallel to the ground. Now the ground is the dashed line that you guys started with, right? His feet are standing on the ground. Okay. Okay, so we've got this laser beam to parallel to ground. It's going to bounce off the surface. Hey guys, is it going to bounce straight back? No, because it's not a flat surface. Is it going to bounce kind of up to the left, do you think? Yeah, right, because it's kind of curving like this, right? Like this what convex is, right? Convex. So it's going to bounce off kind of this way. But how do you know exactly? Right? Well, okay, it's going to follow the law of reflection. It has to do with how tightly curved this mirror surface is. Ah, that's where the focal point comes in. So we're going to go from that point where it's boing bouncing off. We're going to extrapolate backwards to the focal point. And this is exactly the way it bounces off. Boing, just like that. That's the way it goes. Okay. Now, since you guys have looked in plenty of mirrors, you know that the reflection appears to be on the opposite side of the mirror. And what's really going on is that your brain is extrapolating backwards and saying, well, if the light ray came from here, then it must have come from like behind the mirror, which you guys know realize is not true, but it looks that way, right? The reflection looks like it's on the opposite side of the mirror, right? So now I dashed this just to say that there's no actual light there, but that's what your brain would interpret like, oh, well, light ray must have come from over there, right? You guys get that? Okay, so everybody's got that so far? Okay. So all I've done so far is parallel to the ground, skirt the top of his head, parallel to the ground. Okay. Then it boing bounces off in a way that aligns with the focal point. Okay. And you can extrapolate back to Earth. You guys get that? Okay. All right, well, that's not enough by itself to figure out where the image is going to be. That could be one point of evidence, right? So I need at least another ray of light. So let's go from one more thing I want to mention, which is kind of a good segue too. If you shone a laser light here, it would boing bounce off this way. But if you shone a laser light like from this direction, it would boing bounce off parallel to the ground again. Okay, that's kind of what we're about to do here. What if you shone a laser light right skirting the top of his head, but it was aimed at the focal point instead of being parallel to the ground? Well, what's that going to do? Well, let's try it out. So here comes the laser light, and then right there. Now, of course, it's aimed straight to the focal point. That's how I lined it up. Okay, but that's going to bounce off a boing parallel to the ground. So right there. Okay, and then hold your ruler in place for your straight edge and extrapolate backwards behind the mirror. Looks like that. Okay. Okay. So hopefully you have that. If you're having trouble following, here, give you guys a recap. Okay, so the first line I did was parallel to the ground, top of his head. That was a number one. That bounced off a boing in a way that aligned with the focal point. So that's line number two. Okay, so we got that. Extrapolate backwards. And then we started over and said, hey, what if you shine a light skirt the top of his head, aim straight to the focal point? Well, that one's going to boing bounce off back parallel to the ground, and then you can extrapolate that one behind the mirror. Okay. Now, do you guys see where these lines all converge? But besides the focal point in the top of his head, it's also at this point, bam, right there. Okay. Which would also be the top of his head in the reflection. Okay. Now you can also do the same thing for his feet, but that's just going to bounce back and forth with the floor. So you can figure out the whole thing just from what we've done. So here you go. There is the image right there. I'll go ahead and label so we know what's what. Label this guy the object. Okay, and label this guy the image, and I'll even specify it'll be what's called a virtual image. Virtual image. Right, just to distinguish it from later on what's called a real image. Virtual image just means it looks like it's behind the mirror. Right? Real image is like what I just passed around the class, where it looks like it's hovering in front of the mirror. Okay, but we'll get to that later. Okay, you guys get that? So that's what you'll see anytime you look at the backside of a spoon. You see a reflection of yourself that's smaller, but right side up. Appears to be on the opposite side of the surface. Okay. Okay, have we got that? All right. So this next one, what if you either back the spoon further away from your face, or if you make it more tightly curved, which are kind of the same effect. And if you sit down and think deeply about it. Or here, how about this? What if you take this focal point and just move it like closer to the surface, right? It can either represent a more tightly curved spoon, right? Or some version of like holding it further away from yourself. Because you get right up close to it, it's close to like a plane situation. So here's the focal point. Okay. And also back the object up further away. Right? So it's similar effect. Right? So here's the object now. Put his feet on the floor, the whole deal. Okay. And let's go through the exact same procedure and figure out where the image is going to be. Right? So what happens if you back the spoon away from your face? What does it look like is going on? Okay. Right. So same procedure we just did. Shoot a laser light just skirt the top of its head parallel to the ground. Here's your first line. You guys got that? Top of its head parallel to the ground. That's going to boing bounce off in a way that aligns with the focal point. Boing, just like that. Now I'm going to extrapolate backwards behind the mirror. You like that? Okay. You guys good? Okay. Okay, so that's that ray of light. Boing or boing. Okay. But remember what we did after that is we started over at the top of his head and aimed straight for the focal point. We got this laser light, we're going to aim it down a little bit, aim straight for that focal point. Of course, once it hits the mirrored surface, it doesn't actually cross the mirrored surface, even though we're aiming for that focal point. It's going to boing, bounce off, parallel to the ground. Okay. And that one I'll extrapolate backwards behind the mirror. Just like that. Okay. Or if you'd like, if you had aimed a laser light parallel to the ground at that point, it would have boing, bounce off and just skirt the top of his head. You guys got that? Okay. And you guys see where those rays cross behind? Okay. Well, at the top of his head here, his feet are still going to touch the floor. The whole process does, but it ends up being pretty much the same scenario as the first one. I mean, it's not categorically different from what we just did before. Right? There's still a virtual image. Right? Virtual meaning it looks like it's behind the mirror. It's still right side up. Okay, so going from the first picture to the second picture, the further away you hold the spoon, right, it just looks like you get smaller and smaller, right? And it's but the distance looks like it's sort of approaching the focal distance of that spoon curvature. Right? Good so far? Okay, let's do one more, and then I'll break out that equation, and then we'll flip over and do concave later. All right, so this third one, what if this third one has very little curvature at all? What if it's like so uncurved that it's almost a plane. It's almost a plane mirror, or it's like approaching a plane mirror. Okay, I was thinking about this. Go back to this here. Okay. If you have a plane, suppose it is a perfect plane. How big a circle would it take to fit flush to a plane? Infinite. You need an infinitely large circle, would you? Okay. So if the radial size is infinitely large, then what is the focal distance? Also infinitely far away, because half of infinity is still infinity, right? Right. Now, if I want to put the focal point kind of on this page, the best I can do is just to squeeze it all the way at the right side of the paper. That could be the focal point. Okay, so this is not a true plane, but it's kind of as close to a plane as I can make it for a convex mirror. Right, guys get that? And let's put this object, let's put it right about here. Object. Okay. And I want to do one that approaches a plane because you guys know exactly what it should look like in a plane mirror, either because you just saw Paul Hewitt do it a few minutes ago, or because you're brushing your teeth every morning and you're looking in a plane mirror. Right? You know what the outcome's going to be pretty much. Right? And this should be pretty close to that. But we're just going to do the same procedure that we did for the first two. It's going to follow a couple of rays of light. So let's go one ray of light, skirt the top of his head parallel to the floor. That's going to boing, bounce off. But notice I don't have to turn the ruler very much, because if it was a true plane, it would just bounce straight back. And this is not very different than that. Rotate a few degrees, like extrapolating backwards. Extrapolate back towards this focal point right here. Okay, just like that. Boing. Same as the first two. Okay. And the other thing we did for the first two was we went from the top of his head straight for the focal point. Okay. Dash all this. And that would boing, bounce off parallel to the ground again. Of course, all the light rays are really on the left side of the mirror, but oh, I forgot to do one thing, which is I'm going to extrapolate that last ray segment back behind the mirror, okay? Because your brain would interpret, well, that light ray is traveling in this direction. It must have come from behind the mirror. Okay? Tricks your brain. I think there's something going on over there. Pretty sure. And look where those rays cross behind the mirror. Bam, right there. Image. It's also a virtual image, you could call it, just like the first two. Oh, look at that. Right. Again, this isn't an exact plane, but it's approaching a plane. And you guys see how the image and the object are almost exactly the same size? Right. And also they're almost equidistant too from the surface, almost the same distance. Right, you guys see that? Okay. Okay. Let's do some math. All right, so here's the equation that should align with these ray diagrams. So what I'm trying to say is that what we're about to do with this equation, 1 over the focal length equals 1 over distance object, 1 over distance image. This is an equation form of this graphical approach to tell you where the reflection is going to be. Okay? And we're going to see how close this is. It should be pretty close. So 1 over focal distance equals 1 over distance object plus 1 over distance image. Okay. All right, so the first picture, we'll do all three of these. All right, so the first one, looks like the focal distance was almost exactly 10 centimeters. I just made it random, but that distance right there is like 10 centimeters. Okay, so I'm going 1 over 10 centimeters. One more thing. Actually, there's one more detail I have to add to that, which is some of these things are on the right side of the surface, and some things are on the left side of the surface. I'm going to define the object as being on the positive side, which in this case, like for this convex mirror, means the focal length is going to be on the negative side. So this isn't 10 centimeters, it's going to be negative 10 centimeters. Okay. The object, I'll define as the positive side. Let's see, where's the object? The object I've got as maybe 2.7 about centimeters. Be 22 and a half and 3. I'll call it 2.7. Okay. So 1 over 2.7 centimeters. Now that's probably not true on your own paper because just mark this up, but follow along if you want to. Start both of it. Okay, and then plus 1 over distance image. Okay. So let's solve for the distance of the image, which should be some negative value. Okay. Then we'll go back and measure it and see how close it is. Okay. So actually, we'll try it the other way. Okay, where does my image look like? It's going to be looks like about negative 2.5 centimeters, I think. 2.5 centimeters on the negative side. So hopefully I get something close to negative 2.5, but we're gonna find out. So I'll take 1 over negative 10. Okay, 1 over -10. We're going to subtract 1 over 2.7, and then take the reciprocal of that. Cut through some algebra here. Getting distance image is -2.13 centimeters. Oh, remember I just measured it, that it looked like it was about -2.5 centimeters on my paper. That's really close to that, isn't it? All right, so that is good. That is good. All right, let's try it for the second one. Should work. Right? In fact, if you kind of follow a pattern, that's one thing I want you to get out of the class in general. Is like, play around with variables in your head. You guys can see a variable here. You're just like backing up away from the spoon. It looks like the image is approaching like this focal distance. That's what it looks like is going on. So let's see if the equation version of this lines up with that. Okay. All right, where's my object? My object is about a little over 8. It's like 8.2 maybe centimeters, 8.2 centimeters, I'll call it. So oops, sorry, that was the object. 8.2 centimeters goes there. Okay. The focal distance is the other thing I need to measure. Okay. And this is looking like a 4.5, I think, 4 centimeters. So -4.5 centimeters. Okay. Plus 1 over distance image. Okay. So we'll solve for that. Let me see what it should be. So according to my graphical answer, it's a little over 3. Maybe we'll call it 3.2-ish about centimeters. And also negative. Okay. Let's see if I get something close to -3.2 centimeters for this guy. So 1 over -4.5 minus 1 over 8.2, then take the reciprocal. Right, so I'm getting distance image is -2.91 centimeters. Yeah. It's really close to what I was saying. Okay, I was saying -3.2 is what I said, -2.9. All right, like 3 millimeters off. Okay. So that's almost a perfect match. Okay. That's good. Okay, and then what about for this third one? Now for this third one, for the math, I actually will pretend that it's a plane mirror because it's pretty close to that, right? And I kind of want to make this point about what the plane would be. Yeah, so how are the numbers going to be then, right? 1 over focal distance is 1 over distance object plus 1 over distance image. Okay. And what do you guys say the focal? Infinity, right? The focal. There you go, right? Because mathematically, I'm treating the focal point is infinitely far away. Right? That would be a perfect plane mirror, right? Right. So like a plane mirror would have an infinitely far away focal point, focal distance. Okay. The object. Actually, it's negative infinity, but same result, right? It's about 2.5 centimeters. So I'll call this 2.5 centimeters. Okay. Plus 1 over distance image. Okay. All right. And you guys heard what Stephen said this fraction was equal to, but 1 over infinity or 1 over negative infinity. What is that equal to? It's 0, right? 0. Right. Here, this trips up a lot of students, but this is a good thing to know before you graduate high school. Here, I'll give you guys a couple examples. Suppose you turn 18, you graduate high school, you go buy a lottery ticket. And you say, oh, I have a 1 in 20 million chance of winning. Is that really good or really bad? It's bad for you because realistically, it means your chances of winning the lottery are very close to 0, which is what this is. This is pretty much 0, isn't it? Okay, 1 over infinity 0. Right. And if that doesn't make sense, how about this? What if you just start plugging in fractions? 1 over 5, 0.2. 1 over 50, 0.02. 1 over, I don't know, what is that? 1 over 10 million, 0.000. Okay. You guys see the larger the denominator, the closer this result gets to 0? You see that? Okay, so same idea. So 1 over 2.5 centimeters plus 1 over distance image. Now, either by symmetry or you could do the algebra. You're going to get distance image is -2.5 centimeters. Okay. Which just means that the image is the same distance from the surface as the object, just on the opposite side, which pretty well aligns with that picture. Right? Okay, you guys it? Okay, everybody good? Right, so we got a graphical approach, but we also have an equation approach to tell us where the reflection is going to be. Right, yeah.
Just to help you remember, the D0 and the D1, how do we measure them?
Okay, so D sub O stands for distance to the object. Right, we're going from the surface. So, okay, so DO is distance of the object from the surface, and D sub I is distance of the image from the surface. Okay. And the focal length is from the focal point to the surface. So, on
Is that measuring along like the x-axis or along that line that we draw?
yeah, I'm drawing along the x-axis. Although, yeah, they'll be slightly different because of the curvature, but they're pretty close to each other. So like this one here, from this object to the surface of the mirror. Yeah, I've just been going across the floor. That's what I did. Okay. Yeah, maybe you're right. It wouldn't be exactly true. You know, if you're they go up a little bit, it'd be off a little bit, but something like that. Okay, and then from the surface to the image, and then from the surface to the focal point, that's it's the image just in the focal length.
So you don't measure the diagonal line.
Oh no, you're not measuring at an angle. No, all right. You're just doing like parallel to the floor. Yeah. Like that. All right. All right. So you guys go with those three? Oh yeah.
What if you take the object, it's a mirror, and you put the two mirrors facing each other? Thing like the infinite thing.
Oh yeah, you can get like you call it like an infinity window or something. Yeah. You can do that too. An infinity mirror. Yeah. Let me see. I think I gotta let's see if I can find a video on that. Yeah, let's switch my screen over here. Show you guys. Find that. All right. Because Vsauce video is pretty good. At some point, it sets up an infinity mirror. Here it is, mirror tunnel. Right. Yeah, you can see how like the further back you go, it gets like more and more of a green color. Right. So one of the points to trying to make in this video is that right, mirrors actually absorb a tiny bit of light, and they reflect the most in the green color of the spectrum. So yeah, if you set up a mirror tunnel, you'll get like more and more green back there. Ooh, there's a better version. Right? Yeah, it's like a mirror tunnel. There you go. All right, so now let's switch over and set up some concave mirrors. Now, concave parabolic mirrors. That's like what I passed around with the Mirage Pig. Looks like it's floating in front. Okay. So let's do ray diagrams for concave mirrors, which is still like reflection. Yeah. So we're still doing reflection. Okay. We'll save refraction for a different day, but we're just doing reflection. Reflection. Okay. And we're going to do 3 examples here too. Okay, so I got a dashed line to represent the floor. This is kind of right across the middle of the paper, about a quarter of the way up. Got a floor right here. And about a quarter from the bottom, up another floor. So 3 examples for concave mirrors. Now, concave is, I think, a bit more interesting because you can get different categories of answers depending on where the object is compared to the focal point. Okay. But like the 3 that we just did are kind of categorically sort of the same thing, or pretty close to each other. Okay. But that's not going to be true for what we're going to do here. So let's go mirrored surface like right here. Actually, the second one I'll do like the same thing. Okay. And this third one, let me do this. I'm going to back up the mirror to about the middle of the page and make it a little bit bigger. About like that. All right. And throw a focal point right here about focal point. Let's go back that focal point further away, like right here. And then this third one's put like way the heck over here. All right. And so this is like a cosmetic mirror situation. Actually, I think I got a cosmetic mirror like right here. well, one of these is, right? So yeah, a couple of mirrors. No, this one is like a flat plane. This one has like a little bit of a concave curvature to it. I always remember like concave being like you can walk into a cave, right? Like it's open like this way, right? So the surface is kind of like that. Right? Put a little bit of water, it would like hold the water, like a little puddle in the middle. So and the purpose of this thing is so it should like blow up your face and make it look bigger. Okay? But it depends where your face is. So you gotta get kind of close to the surface. Okay? You guys can see that too. Okay, so this first one, let's put the object. You guys see that focal distance, whatever that is. Okay, let's double that, and then add a little bit more distance. So I took that focal distance, I'm gonna double it, and add a little bit more distance. And I'll put the object like over here. There's the object. Okay. For the second one, let's put the object right on top of the focal point. And for the third one, I'm going to put the object kind of closer to the surface, like right about here. Okay. Actually, what was passed around class, you can take those parabolic mirrors apart and swap around, and you've got kind of like a cosmetic mirror situation. And if you hold it really close to your face, it's like this third scenario. If you hold it really far away from your face, it's kind of like this first scenario. And if you put it just the right point, you can put your eye, like your eyeball, right on top of the focal point and get a really weird outcome. Right? But let's see graphically what that should be, and you can test that out too. Oh, actually, I got a ton of these. Let's forget about this guy. It's got a flat mirror on that side and like a concave mirror on this side too. So there's a bunch of these going around. So we're going to follow the exact same rules, graphical rules that we did for the other side of the paper. So let's go. One line is parallel to the ground, just skirt the top of this guy's head parallel to the ground. Okay. And that ray of light is going to bounce off through the focal point. Right? Okay, so that's one ray of light. Okay. Remember, once we get the second ray, we can see where two rays are going to converge and post exactly where the image is going to be. Okay. So let's go back to the top of his head and aim this laser straight through the focal point. And that one's going to bounce off, boing, back parallel to the ground. See where they cross right there? Okay. Now that's the top of his head for the image. His feet are still going to be on the floor. I mean, you can do the whole thing for his floor, just for the feet on the floor, just going to bounce back and forth. So there's the image. Now, do you guys see how the image is on the same side as the object? And also it's inverted. Okay? So the fact that it's on the same side, I'm not going to call it a virtual image. I'm going to call it a real image. Okay? And the fact that it's upside down, I'll call it inverted. So this is going to be an inverted real image. Inverted real image. Okay? Inverted because it's upside down. Real because it looks like it's hovering in front of the mirror, just like the demo that I sent around. So this is how the floating pig works. Okay? Well, really, it's like two of these, but it's the same principle, same idea. Okay? It's like a double reflection, sort of. Okay, got that? Okay. We've got about a minute left of class, so can you guys save this paper so we can finish these two tomorrow? Okay. Or give you guys a day to think about it too. All right, so that'll be a pause point today. I'll eventually have you guys turn this in, and as long as you have the same diagrams that I do, I'll give you guys some points in the grade book. Okay, good. Probably have you guys turn this in tomorrow.